Hello ladies and gentlemen, my name is Ara Abulyan and today we are going to talk about continuity. So what is continuity and what are we dealing with? We want to deal with functions and we want to determine whether functions are continuous or not continuous. There are three different types. So this is the first one. We have our y-axis here. We have our x-axis there, so let's call that x and y, and we have a function. And we want to know, is this function now continuous or not? And as it looks like, it is continuous. And that's pretty obvious, but another way how to explain it is if I were to draw a little man up here, and he would walk down the graph, or up the graph, and he would walk, and he would continue and walk and continue. He would eventually still continue, right? And therefore this is a continuous graph. There is no cut anywhere that he can just continue walking on that graph. Here's the next scenario. So let's say y and x and function, and something is happening. Okay? Obviously it's not continuous now, but once again, our little man up here is walking down the graph, walking down the function. He continues walking and he still continues, and he continues and continues and walks, continues until here. Now he can't continue anymore. If he would fall down, right? He would fall down here. So of course he doesn't want to fall down, and what's happening here actually? In order to continue his path, he would have to jump up here, right? So guess what the name of this discontinuity is? It is a jump discontinuity. So, in a more mathematical explanation is that our function jumps from this value, y value at this point A, for example, to another y value. And there's another case too of discontinuity. So that is this one. X and y and function and more function. And right here, let's say something like this. So what's happening right here? Is it continuous or not continuous? Let's draw our little man, and he walks. He's taking a walk, and he walks and walks and continues walking and walks until here, right? If he would walk, keep going, he would fall down. So what's happening right here in this area? As it looks like that this little gap here, this little way, this little path has been removed to another place. It's here, right here, right? It looks like this point should be here. It's not. It's here. So it's somehow not continuous. So that's why this kind of discontinuity is called removable discontinuity. This little part has been removed up there. So we can't continue right here anymore. Too bad. So these are the three different cases. We have a normal continuous function, we have a jump discontinuity, and we have a removable discontinuity. Now some instructors say, here are some functions, and tell me whether these functions or that one function at the end is continuous or not, and show me that without graphing. So what we did was graphing, right? So in order to show it without graphing, we would have to know some conditions, some rules. There are three conditions. So let's start with the first one. Let's write it right here. First condition is going to be our limit as x approaches a of f of x must exist. That's all. Must exist. Okay? That is our first condition. Now the second condition. Here it is. F of A must exist as well. That's it. Must exist as well. Okay. Now the third condition. It's not too hard. It's our limit as x approaches A of f of x must be equals to f of A. And that's it. We have these three conditions. And our f of A, if it exists, must be equals to this limit. And it kind of makes sense, right? Because if we, again, a visual explanation, if we would draw a function here and we say that this is our A, and we're going to have here our f of A, and this function is our f of x, okay? We say at different x's, so our limit as x is approaching A, which means what is the value of our function as we go from the left side and from the right side, from both sides. What value do we get? That must exist, so that's this part. F of A itself at this point, exactly at this point, must exist too. So that's this case. If you're asking, well, it can only exist, no, it does not have to be. It could be like this, for example. It would just not be defined, right? So it would not exist in this case. But it has to exist too. So yes, it exists. And the third case, it says our limit of as our x approaches A of f of x from the left and from the right side, that value here must be equal to f of A, our actual value of A. And it makes sense. How could these values be the same and our actual value at this point be up here? Obviously it would not be continuous, because our little man would walk here and he could not continue because our actual value of A is up here. So that wouldn't work. So far to the visual explanation. We have the three rules up here, and I wrote it already down. We have some functions here. So we have x minus 1 under the condition our x is less than negative 1. We have x squared minus 3 when our x is between 2 and negative 1. We have 3, which is where our x is equals to 2. And we have 3 minus x where our x is only greater than 2. So how would we start? We would have to know first a point to determine whether our function is now continuous or not. So because we have a function and we could say at any point we need to lower our domain, right? We have a function. We have to say, okay, at this point we want to know whether our function is continuous or not. Or we would have to say, at this point we want to find out whether our function is continuous or not. In this case, it says in the question, when x is 2, we want to find out whether our function is continuous or not. So 1, 2, it would be here. So we don't want to do this graphically. We don't want to do this numerically. We want to do this algebraically. So what's happening? We would have to start with the first condition, right? We would say, for example, number 1. And let me sit down here. We would say 1, and it says limit as x approaches A, or 2 in this case, of f of x. So we remember that if we say as x approaches to A, we have to come from the right side and we have to come from the left side as well. So we would say as x approaches 2 from the positive side of f of x, which is going to be from the positive side, right? So x must be greater than 2. Greater than 2, here our x is less than negative 1, our x is less than 2, our x is equals to 2. oh, right here, x is greater than 2. This is what we want. So it's 3 minus x. So it's 3 minus 2 in our case. This must be equals to our limit as x is approaching 2, and this time from the negative side. Let me write this a bit bigger, I think, so you can read it probably better. Limit as x is approaching 2 from the negative side. So now from the negative side, so what does that mean? X must be less than 2. Where is our x less than 2? We have here x is less than -1, here our x is less than 2. This sounds good. So let's use this function. We would have 2 squared minus 3. So what values are we going to get? 3 minus 2 is 1 equals 2 squared minus 3 is 1. So this looks good. And our first condition is met. Limit as x is approaching 2 must exist. And it exists. Second case. Second condition, sorry. Our f of a must exist. So what is our a? It's 2, right? So f of 2 must exist, which is here, f of x. So f of 2 now, at right 2, that should be this one, right? X equals 2, exactly at that point. So, sorry, this one. So that is when our f of our function is 3, x 3. So we would write f of 2 equals 3. And that's it. Condition 2 is met. So these first 2 conditions are done. We are almost done. Third condition. Our limit f of x, so our limit, let's write x approaching 2 of f of x, so which is 1, must be equals to, right, equals to f of a. And our f of a is our f of 2, which is 3. Good. Is 1 equals 3? No, it's not. So what kind of discontinuity would we have here? So if we want to visualize one more time, let's say we have our x here and our y there, and somehow our function, this is probably not how it would look like, but just for example, we have a function, and then here at this point we have 1. At this point our function somehow continues. We have another one. Yeah, these are these 2 ones from the left side and from the right side. We get the 1, and this is our 2. Okay, 1, 2, and at 2 we have 3. So 2, 3. So that's not cool, because as it looks like, if our man would walk the function down and continue walking, right here he would fall down. In order to continue, he would have to jump up and jump down again. In other words, this is a removable discontinuity. So far to the topic continuity. I hope you could understand what I was trying to explain, and I hope you somehow enjoyed this video. Thank you very much.